What is up, guys? This is one of my last videos for this year. Isn't that crazy that we're almost done? This could be the last one. I don't know. We'll see. But this section we are looking at theoretical probability of simple events. So do you know what the word theoretical means? Kind of means like what would happen in theory, like not an actual thing, but like in theory, what do we expect to happen? What would we expect the probability to be? But before we get into that, we're going to talk about some more terms you need to know. So we've already looked at some things like relative frequency, frequency tables, and things like that. So you're getting lots of maybe new words in this section, in this chapter. But another term that you need to be familiar with is sample space. So in a probability experiment, set of all possible outcomes is the sample space. And to find the sample space, you can just make a list of each unique outcome. So for instance, one experiment would be rolling a die. The sample space is all the possible outcomes. When I roll a die, I could get a 1, a 2, a 3, a 4, a 5, or a 6. So the sample space is just a list of all of the outcomes of an event. And by the way, this is on page 529. So if you're wanting to take notes, which you should be, because that's what I'm checking to make sure you are watching this, 529 is where you want to start. So suppose we roll a number cube 10 times and recorded what we get. So here's all of our 10 tosses, and one time we got a 2, 3 times we got a 3, and so on and so forth. Then the relative frequency of rolling a 1 or rolling a 6, no. Oh, in the book, okay, so in the book this is a 0. They have different numbers in the book than here. So look at the numbers in the book, ignore these numbers, use the ones that they have in the book on page 529. The relative frequency for both of these, we didn't get a 1 at all, so the 0 out of 6. But our sample space is still 1 through 6, even though we didn't get those in this. All possible outcomes is always listed in your sample space. And each time you roll, there are still 6 possible outcomes. Even if you might not get that outcome, they're still there. So if you want to find the sample space, this is on page 530. Each letter in the word mathematics, isn't that a beautiful word? Like probably one of the best words you've ever heard. Is written on a piece of paper and placed into a bag. And I can tell which ones of you right now are like, no, boo. But it's a great word. A letter is drawn at random. What is the sample space? So the sample space is just a list of all the possible outcomes. But when we talk about sample space, we want unique possible outcomes. So since some letters repeat, the outcomes in the sample space are each unique letter that appears in the word. So if you think about it, we would use each letter only once. So there's only one M. We have an A. We have a T and an H and an E. We already have an M in the bag. We already have an A in the bag. We already have a T in the bag. We don't have an I. We need a C and an S. So the sample space is these letters here, all of the letters in the word mathematics, but only listed once. Okay. So now when we talk about the theoretical probability of a simple event, let's go back for a second. Sample space, just a few other things. Sample space here for this spinner would just be red, green, blue, yellow. All the possible outcomes. If I spin the spinner, what could it land on? Red, green, blue, and yellow. So that's my sample space. If I flip a coin, my sample space is heads and tails. So that's just, you're just listing all the possible outcomes of an event. Now the theoretical probability of an event, okay, is based on uniform probability, which is an event in which all the outcomes are equally likely. I don't know why this keeps saying this for me. Theoretical probability is essentially what we expect to happen. So again, it's the ratio of the number of favorable outcomes to the total number of outcomes. It's the same as our relative frequency. It's the same as our, what else did we call it? experimental probability. A lot of these things are kind of all the same thing. So let's see. So the other part's not showing up for me for some reason. So if you look on page 531, the probability and under ratio, again, is the number of favorable outcomes over the total number of outcomes. And kind of like we looked at the other day when we looked at likelihood in the very first section, we can see kind of the probabilities that might go along with each likelihood here. So let's see, anything? Oh, here they are as a fraction. Like here would be the probabilities as a fraction. 0, if something is impossible, it has a probability of 0. If something is certain, it has a probability of 1. And then equally likely would be 1/2, and then kind of in between there as well. So these are just our values for theoretical probabilities. So again, continuing on page 531, if I toss a coin 20 times and record the results, okay, 20 coin tosses, then the relative frequency of tossing heads is 17 out of 20. The relative frequency of tossing tails is 3 out of 20. But because each outcome is equally likely to happen, the theoretical probability is 1/2. Okay, so this is what happened in actuality, but in theory, this is what we would expect to happen because there's one of each. So now, why are the relative frequencies so different? Well, again, this is what you should expect when conducting, while the relative frequency describes what actually happened. And in the next section, we'll talk about when the relative frequency should be pretty close to the theoretical probability. So look at example 2 on page 532. 8 discs are marked, 3, 4, 5, 6, 7, 8, 9, 10, such that each disc is marked with exactly one of these numbers. A disc is selected at random from the bag. What is the theoretical probability of selecting a disc marked with a prime number on it? So first of all, this is my sample space, 3, 4, 5, 6, 7, 8, 9. These are all the possible outcomes, and 10. There are 1, 2, 3, 4, 5, 6, 7, 8. So the total number of outcomes is 8. So that will be my bottom number of my probability. And then how many of these are prime? 3, 7, 5, not any even numbers, and 9. So there are 3 prime out of 8 total. So our probability of a prime number is 3 over 8, which is 0.375 or 37.5%. So again, the theoretical probability, what we would expect to happen in theory, is that I have a 3 in 8 chance of pulling a prime number out. But if I did this 8 times, would I get exactly 3? Not necessarily. So that would be my relative frequency, but it's not necessarily the same as the theoretical probability. So try the check problem on page 532. Pause this and do that. And if you didn't already, do the one on page 530 as well. And then unpause it, and we will continue on page 533. So when we talk about events, something like rolling an even number, a success, if I roll a die, would be rolling an even number, and rolling an odd number is not a success. And these events are known as complementary because they can't happen at the same time. So when we talk about complementary events, there are 2 events in which either one or the other must happen, but they cannot happen at the same time. The sum of the probability of an event and its complement is 1 or 100%. Now, if the probability of an event, I would like the symbols to come up. If we use PA to represent the probability of an event, then the complement is written as P not A, or we generally use A prime. A with this exclamation point, we call it A prime. So PA is the probability of the event, PA prime is the probability of the complement. Some textbooks actually also use like a line over the top, like this. So that also would mean the complement of A. So depending on the textbook, yours uses this, but this means the complement of A, or this means the complement of A. So for instance, if the event is tossing heads, then the complement would be tossing tails, and they can't both happen at the same time. So that's what we're talking about when we talk about complement of an event. Now, a probability plus the probability of its complement is always equal to 1. So for instance, what's the probability of rolling a 1 on a die? There's a 1 in 6 chance. What's the probability of rolling not a 1? Well, there would be a 5 in 6 chance, right? And 1 6 plus 5 6 equals, dun dun dun, 1, yes. So, does that make sense? What a complement is, and that the probability of an event plus the probability of its complement will always equal 1. So for the last example in this video, go to page 534. And on 534 you see a table. There it is right here. Raphael is going to ride a roller coaster chosen at random. So there are 1, 2, 3, 4, 5, 6, 7, 1, 2, 3, 4, 5, 6, 7, 8 roller coasters, and wants to find the probability of choosing a roller coaster with a height less than 250 feet. What is the probability of the complement of the event? So first, what is the complement? Well, he wants to choose roller coaster less than 250, so the complement would be not less than 250. So basically, greater than or equal to 250. So the first thing we want to do is identify the complement, which we did, and then list all of the outcomes that make up the complement. So find all the roller coasters with a height greater than or equal to 250 feet. So that would be, I don't know if this is going to work for me, but you can see here, we'll just do this by hand. This one, this one, this one, this one, this one. So how many are greater than 250? There are 5 of them out of 8. Oh, there we go. So there are 5 outcomes that make up the complement. And then the probability of the complement would be 5 out of 8 total roller coasters, 5 out of 8. So there's a 3 in 8 chance he selects one that's less than 250. There's a 5 in 8 chance that he selects one greater than 250. So see if you guys can do the check problem on the bottom of page 534. And some of this might not make sense yet, but hopefully you get at least a quick introduction to some of these topics, and we will definitely be spending some time in class going over this in more detail, and you guys will become experts at theoretical probability by the time we are done in class on Friday. Okay, have a good night, evening, afternoon, morning, whatever time it is that you are watching this, and I will see you soon.